Hello everyone, so I'm back with another new video. I was discussing NMR spectroscopy, how to analyze the proton NMR signals for the compounds we make in our lab for organic synthetic chemistry research. So please watch my previous videos to know about the fundamentals of the NMR spectroscopy, how to analyze the proton signals, the fundamentals. I have discussed them in details in my previous videos. And now I will be discussing more examples like I will pick up a structure and I will discuss how to analyze its NMR signals. I will show you the practical NMR data which I have got in our lab. So let's get started. Let me share the screen. So I hope you can see the screen now. So in my NMR spectroscopy series, I think this is my fourth video, but this is mainly about the practice NMR. I'll show you different structures and I'll teach you how to predict the NMR of that structure, and then I will show you the NMR spectrum for that compound which I got in my lab. Okay, as if you do not know about details of my research area, please check these links to know details about my research area. Okay, so let's get started. So this is the structure one. uh, so what we do in our prediction NMRs, we majorly look at the aliphatic protons and the aromatic protons. In my previous video, I have already discussed in details about the chemical shift values, uh, like which type of proton will have a chemical shift value around what, like the number. But mainly, broadly, we look at aliphatic protons and aromatic protons. Okay, so the aliphatic protons have their chemical shift value within 1.5 to 5, and the aromatic protons, they have their chemical shift value within 6 to 8. Okay, so let's check in the structure how many different types of protons do we have. So we have 1, 2, 3, and 4 different type of aliphatic protons. So 1 is for 2 aliphatic protons, 2 is for 3 aliphatic protons, and 3 is again for 2 aliphatic protons, and 4 is for 1 aliphatic proton. So we would expect a signal corresponding to 2 aliphatic protons, another signal corresponding to 3 aliphatic protons, another signal corresponding to 2 aliphatic protons, another signal corresponding to 1 aliphatic proton. All of these signals should have a chemical shift value within 1.5 to 5. And let's check how many aromatic protons do we have. 1, 2, 3, 4, 5, 6, 7, 8. So there are total 8 aromatic protons, and their chemical environment are maybe slightly different or whatever, but their chemical shift values are usually very close. So we do not check for different type of aromatic protons. We broadly see how many aromatic protons do we have. So there are total 1, 2, 3, 4, 5, 6, 7, 8 aromatic protons. And so we'll see maybe one signal, maybe two signal, maybe three signal corresponding to 8 aromatic protons, which will have a chemical shift value within 6 to 8. So now let's look at the actual NMR which I got in my lab for this compound. So okay, so this is the NMR which I got for this compound. So as I mentioned, we would expect a signal for two aliphatic protons. Let's check where is that in the NMR. So yeah, so one we have a signal for two aromatic protons. Here the number you can see 2, 2.08, 3.09, 1.03, 9.31. These are all the number of protons. Whenever you take a NMR spectrum, you will have an option to integrate the peak. In the NMR software, you will have that option, integrate the peak. So I have integrated the peaks, and these are the corresponding integrals, and this signifies this peak is for how many protons. So this peak is for 2 protons, this peak is for 2.08, and this is for 3.09, and this is for 1.03. So as you can see, all of them are between 1 to 6. So they are all aliphatic protons. And now let's check which I was looking for in my Fredrickson NMR. I was looking for a signal corresponding to two aliphatic protons, and then another signal for three aliphatic protons, and then another signal for two aliphatic protons, and finally another signal for one aliphatic proton. So we have four signals, and they correspond to two, three, and one aliphatic proton. So I have all of the aliphatic peaks present here. And now let's check how many aromatic protons I was looking for. So there was 8 aromatic protons which have chemical shift value between 6 to 8. So here you can integrate these two peaks separately, or you can integrate them together. Most of the cases I have seen they are similar. If you integrate them separately and then add them, or if you integrate them together, you will get similar number of protons. So this is I have integrated here together all of the signals. So it is corresponds to 9.3, but we had 8 aromatic protons. So there is one proton extra. But as I have mentioned in my previous videos, that you have to know which solvent you are using for your NMR. Now let's see, like I have used CDCl3. So I expect to see the CDCl3 residual peaks over this NMR. So CDCl3 has solvent residual peaks around this 7.1 or something. So one of these will be for CDCl3. So that is why I'm seeing the extra peak over here. It should be for 8 protons, but I'm seeing 9.3. So this extra is due to the CDCl3 solvent. If you want to confirm that whether this is for CDCl3 or this is some impurity, so then you have to check this NMR in a different solvent. You can check methanol D. So methanol D doesn't have a solvent peak over here. So you should see a peak corresponds to 8 aromatic protons if you take it in methanol D or DMSO or whatever. Okay. So let's go to the next structure. So this is structure number 2. As I've already mentioned the technique, what we do, we check for the aliphatic protons and aromatic protons. So in this structure, we have 1, 2, 3, 4, 5, 6 type of aliphatic protons. So 1 corresponds to 2 aliphatic protons, 2 corresponds to 3 aliphatic protons, and 3 corresponds to 1 aliphatic proton, 4 corresponds to 2 aliphatic protons, 5 corresponds to 2 aliphatic protons, 6 corresponds to 2 aliphatic protons. So we would expect uh, NMR signal for 2 protons and another signal for 3 protons, another signal for one proton, another signal for two proton, another signal for two proton, another signal for two proton. All these signals will have chemical shift value within 1.5 to 5 ppm. Okay, and let's count the total number of aromatic protons. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are total 9 aromatic protons. So you would expect a signal corresponding to 9 protons, which will have chemical shift value within 6 to 8 ppm. Okay, now let's look at the NMR. So this is the NMR corresponding to that compound. So now let's check what we are looking for. We are looking for a signal corresponding to two protons, three, and then one, two, two, and two. So here, as you see the integrations, we have within this region from 1.5 to maybe 5.5, 1.5 to sometime we get something within 5.52. So this is a signal for one proton, this is for two protons, this is for two protons and another two protons and another two protons and another for three protons. And as you can see, we are using CdCl3, so we'll see solvent residual peaks at this 0, 1.5, and also here in this region. So these are solvent peaks which I have marked here as a tick mark. These are solvent residual peaks. Okay, so we are expecting 1, 2, 3, 4, 5, 6. Let's check here. 1, 2, 3, 4, 5, 6. So we have 6 type of signals which also matches with our prediction NMR. So we have our aliphatic protons matched. Now let's look at the aromatic protons. So we are expecting 9 aromatic protons. So let's check here in this region from 6 to 8. So we have a peak corresponding to 9.6, another peak corresponding to 0.93. So we are expecting 1 for 9. That's fine, but why do we have this extra peaks? So as I have already mentioned that CdCl3 has a solvent residual peak around this region. That is why we're seeing these extra peaks. Okay. So this is another version of the same compound NMR, which the compound was slightly more impure compared to this one. So let's check the NMR of the impure version. So we had all those peaks, like one corresponding to one proton, then another corresponding to two, then another corresponding to two, another corresponding to two, one more corresponding to two proton, and then another corresponding to three protons. We have all those peaks, but we have extra peaks over here. So I couldn't assign this extra peak. And let's check in the aromatic region. The aromatic protons should be 9, but we can see 8, 9, and one more peak. So this is again in CdCl3, so it could be due to the solvent. I do not know, but it may be due to the solvent, but we see one extra peak in this aliphatic region, which I have marked here. I couldn't assign the peak with any of the compound peaks. So this is how we decide whether our compound is pure or impure. Like in your prediction NMR, when you are checking how many signals we should see, and you see all of those signals in your compound NMR peaks, and you see extra peaks, then we decide, okay, then our compound is not pure, we have to purify it again. That is why we are getting those extra signals. And sometimes we get those extra signals due to even some solvents. If you have not dried your sample properly, then sometimes you may see those extra peaks. These are due to different type of solvents you are using during your synthesis and your purification procedure. Okay, so it is very important to dry your compound sufficiently for a long time before you check its NMR, so that you do not see any solvent peak over there, any solvent impurity peak over there. You will always see the solvent residual peaks, like the solvent you are taking, you will always see those solvent residual peaks. If you do not know what are these residual peaks, please check my previous videos. I have discussed them in details. What are solvent residual peaks? Okay, and even if you have dried your compound sufficiently for a long time and you are still seeing those peaks, impurity, these extra peaks, that means your compound is not pure, it has some impurity. So you have to purify your compound again and again check your NMR. Okay, so let's go to the next structure. So this is another structure. uh, as I have already mentioned in my previous examples, we'll look for the aliphatic protons and the aromatic protons. So we have 1, 2, 3, and 4 different type of aliphatic protons. So 1 is for 2 aliphatic protons, 2 is again for 2 aliphatic protons, 3 is for 1 aliphatic proton, and 4 is for 2 aliphatic protons. So we'll expect a signal corresponding to 2 aliphatic protons, another signal corresponding to 2 aliphatic protons, another signal corresponding to 1 aliphatic proton, and one more signal corresponding to 2 aliphatic protons. All of these signals, they will have chemical shift value within 1.5 to, I would say, 5 ppm, but sometimes we see at 5.52, and we see like 1 to 5.5, that would be safe. Okay, and now let's count the aromatic protons. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are total 9 aromatic protons. So we'll expect another signal corresponding to 9 aromatic protons within 6 to 8 chemical shift value. So let's quickly check its NMR. So this is the NMR. As you can see, we have signal corresponding to 2 protons, another for 2 protons, another for 2 protons, another for 1 proton. These are the aliphatic protons. These are what we are looking for. So we have all of these peaks, and now let's quickly check the aromatic region. As you can see, yeah, we have 9 aromatic protons. So this is perfectly matching with our prediction NMR, and here the solvent is methanol D, so we do not have any solvent interfering peak in this region. So this looks clean now. Okay, and this NMR looks very clean. We do not have any extra impurity peaks over here. This is a very, very good NMR. Okay, now let's check quickly our next example. This is the practice NMR 4. So as we look for the aliphatic protons and the aromatic protons, so we have 1, 2, 3, 4, 5, and 6 type of aliphatic protons over here. So 1 corresponds to 3 aliphatic protons, 2 corresponds to 2 protons, 3 corresponds to 2 protons, and 4 corresponds to 1 proton, 5 corresponds to 2 protons, and 6 corresponds to 2 protons. So we will expect a signal corresponding to 3 protons, another signal corresponding to 2 protons, another signal corresponding to 2 protons, another signal corresponding to 1 proton, another signal corresponding to 2 protons, another signal corresponding to 2 protons. All these signals will be within this region, aliphatic region, 1.5 to 5, but sometimes I see from 1 to 5.52. Now let's check the aromatic protons. How many aromatic protons do we have? One, two, three, four, 5, 6, 7. So there are total 7 aromatic protons. We'll expect the signal in this region 6 to 8. Okay. And these protons, these NH protons, these are very tricky. Sometimes I see them in my NMR and sometimes I do not see. Like if I check NMR in methanol D or something, we'll definitely not see these protons. But if I check in DMSO or CDCl3, sometimes I see this proton and sometimes I don't. Okay, so we do not bother about these peaks. We try to match our aliphatic peaks and the aromatic peaks. Okay, so let's quickly check its NMR. So as you can see from these integration values, we have one corresponding to 3 protons, another for 3, another for 2, another for 2, another for 1, and another for 2. So we are looking for the exactly the same thing over here. So but I think this 5 was for 2 aromatic protons, but we see 2.9, which is close to 3. So uh, one aliphatic proton is extra for this. So this compound may be slightly impure because it is not exactly matching. It should be around 2. As I mentioned previously, that if it is less than 2.5, we just assume it is 2. But if it is greater than 2.5, then it is close to 3. So this is not properly matching. Now let's check the NMR for aromatic protons. We have 7 aromatic proton, and here you can see we have 4 plus 3 7. So this region is matching, but we have one extra peak for protons, 1 proton. So it should be 2, but it is 3. So maybe some impurity is there in this compound. So either we have solvent impurity or we have some other impurity. So if you see, like, you have some extra peaks over here which is not perfectly matching with your prediction NMR, then we dry the compound again for a long time and we check the NMR. Sometimes the problem is resolved. We are drying and our solvent impurities are gone. So now we see a good clean NMR. And sometimes this trick doesn't work. So then we check the TLC. If we see the TLC is not a single spot, we have to purify the compound again. So NMR is tricky, right? And it gives you a big clue about your characterization of your compound and obviously about the purity of your compound. Okay, so I will continue my discussion on how to analyze the proton NMRs in my next series, and I will show you more and more examples. Okay, so please like, share, and subscribe to my channel. And you are welcome to post any query in the comment section. I'll try my best to answer all of them. So, thank you.